Hi, Mr. Balogh here. Want to go over the beginnings of integration with you. Now, this is not in chapter 21. I include it here because I want to expose you to it before the book gets to it in the next chapter. And I want to introduce how physicists think about integrals and set up integrals in the context of finding the total charge on objects, instead of trying to do this and also doing it in the context of electric fields, which will happen in the next chapter. So let's get to it. This procedure, this process, this setting up of the integral starts with the thing that you want to find. And so for our purposes, what we're going to want to find is the total charge on an object. The way that we are going to find that total charge is by summing or adding up all the little contributions of charge, little tiny pieces of charge that make up the total. Again, every integral in physics begins this way. What are we looking for? We're looking for the total charge. How are we going to find it? We're going to add up, right? Integrate over a bunch of little tiny representative pieces. And hope the hard part is figuring out what this little representative piece is in the context of a physical coordinate system. Yeah, sure, Mr. Balogh, it's okay. I know the total charge is made up a bunch of little charges. Conceptually, I get it. But how do I get that into a real physical Cartesian coordinate system, polar coordinate system, spherical coordinate system, cylindrical coordinate system? How do I do all of that? Well, the answer is we're going to use density. But we're going to use density in a way that you probably haven't experienced before, or if you have, it's been sort of tangential. What do I mean by that? Well, if you've taken chemistry classes, right, then you know that the volume density of an object, volume mass density, is its mass divided by its volume. But that's actually not the only density that physicists define. We also define something called the surface mass density, which is total mass of the object divided by its surface area. And this is the Greek letter sigma. This is the Greek letter rho. This is the Greek letter sigma. There's a third kind of density that physicists define. We use the symbol lambda and the Greek letter lambda. That's the mass divided by an object's total length. So these three definitions of density are what is going to allow us to link together this concept and idea of, well, what does this little piece of charge look like compared to an actual physical length? So those would be if we were trying to find mass. But what if we want to find charge? Well, we can define exactly the same things. We're going to, instead of using mass, right, we're going to do charge per volume to find the volume charge density. If we want to know the surface charge density, we can take total charge and divide by the total surface area. And likewise, if we want to know the linear charge density, we can take the total charge and divide by the length of the object. It's the ones over here in blue that we're going to be taking advantage of in Physics 4B. But what does total charge have to do with little charge? Well, remember what this little d means here. Okay, you often get trapped into thinking it's some sort of derivative. And while we use the symbol in forming derivatives, what the symbol means, right, is that it's this little dq means that it's a change in charge that's taken place as time, right, goes to a really, really small time interval. And so, in practical terms, right, how do I get from this into this and something I can use? Well, in part, it depends. Are we doing it over the volume? Are we doing it over the surface? Or are we doing it along a line? That's going to change depending on the geometry of our problems. But let's take that volume charge density as an example. We know that the volume charge density is the total charge divided by the total volume. We can rearrange this, right? We can say that total charge is equal to its charge density times its volume. And if I take a little tiny piece of charge, right, a little tiny piece of the total, what am I taking a little tiny piece of? Well, it's not the volume, it's not the density. That's a constant. That stays the same. Density is density, right? Instead, what we're taking is a little tiny piece of this volume. So I would write this as dq. We usually use little q for the little chunk, right? Density stays the same, dv. And here, now we're starting to find something that the integral can sink its teeth into. A volume consists of a length, width, and depth, right? Three different coordinate directions that we can integrate over to find out what's going on. Now, to be honest with you, in physics, we don't do triple integrals or double integrals if we can avoid it. If we can find a way, we will use only a single integral. And I'll be teaching you about that in the videos to come.